Hi everybody, welcome to Chemistry Licious, right? So here we are going to see an important topic in inorganic chemistry, which is Jahn-Teller Distortion, right? So this comes under the chapter of coordination compounds, and specifically it comes under crystal field theory, right? So we need to have certain prerequisites about crystal field theory so that we will be able to go on about it, right? So we are going to take specifically octahedral complexes, because only in octahedral complexes this is going to happen, that is Jahn-Teller distortion is going to happen, right? So now we already know how crystal field theory works. It works with the amount of repulsions between the ligand electron and the electrons in the d orbitals of the central metal atom, isn't it? Right. So when the ligand is not approaching at all, when only the central metal atom is there, I have 5 d orbitals, and all these 5 d orbitals are degenerate. That means they are going to have same energy, right? Now when the ligands are approaching from the 6 directions, right, because of the octahedral complex, now all the energy levels of these 5 d orbitals are going to increase because of increase in repulsion, correct? Now what is going to happen is, now there are going to be 2 types of d orbitals, right? Well, how there are going to be d orbitals where they have their lobes pointing in between the axis, in between x and y axis or z and x axis. Another case where I have the lobes pointing along the axes, and obviously due to the amount of the difference in the repulsions in of these 2 cases, I am going to destroy the degeneracy. That means I am not going to have all the 5 orbitals, d orbitals, to have same energy. They are going to split into 2 sets, one having higher energy and the other having lesser energy, right? So hope you know what are the representations for those. The lower energy set is what is called as T2G, and I know I am going to have the orbitals which have lobes placed in between the axis will come under this, because they will suffer lesser repulsion, lesser energy. And we know what are those d orbitals, that is dxy, dyz and dzx. These have the lobes pointing in between the axis. And when I go for the next one, that is the higher energy level, that is called EG set, and those are going to have the d orbitals which have their lobes pointing along the axis. We know what are these 2, that is dx squared minus y squared and dz squared, right? So this is how the splitting happens, right? Now we'll start with the question, can I have different bond lengths for the 6 bonds I have in the octahedral complex? So the question is, I have a ligand, I have a coordination complex which is octahedral. I know there are going to be 6 ligand metal bond. The question is, can I have all these 6 bonds to have different bond lengths? The answer is yes. And why that happens? That happens because of this phenomena called as Jahn-Teller distortion, right? Now how do we go about it? How is it that I have different bond lengths in the same molecule, same ligand? Even if I have same ligand, same metal atom, the bond lengths are in certain cases are going to be different, and that is going to happen because of some specific cases where I can have the electronic configuration contributing to extra repulsions, right? Now for us to understand this, I would say that there are going to be 2 types or 2 ways by which I can have a electronic configuration. First case is what is called as symmetrical filling, that is symmetrical electronic configuration, right? So like as the name tells you, I can directly go with an example. Say one case of symmetrical filling can be like this, right? So 3 orbitals, each of them having 1 electron, 2 orbitals, each of them having 1 electron. Or there can be other case. This is also a symmetrical filling case. 3 of the orbitals have 2 electrons and 2 of these orbitals have 1 electron each. Or this can also be a symmetrical case. 3 of them having 2 electrons, 2 of them having 2 electrons each, right? Or this can also be a symmetrical case. So I have 3 of the orbitals having 2 electrons each, and in EG set there is no electron at all, both of them having 0 electrons, right? So these are all the cases where I have symmetrical filling. So whenever you have symmetrical filling, you don't have to worry about the bond lengths. All the bond lengths are going to be same, no problem at all, right? But when I go for the next type of filling, that is my unsymmetrical filling, right? So what can be examples? Say some, like one case can be like this, right? And say another, like you can see that 3 of the T2G set is having 1 electron each, and here when I go, one of the EG orbitals is having 1 electron, the other one having no electron, unsymmetrical. Or the other case can be something like this again, or sorry, something like this, isn't it? Again you can see that T2G is no problem. When I go to EG, one of the orbital is having 2 electrons, the other orbital is having only 1 electron, again unsymmetrical case. Now I would say these two are the only cases possible. Now the next question immediately comes to your mind is, what if I have unsymmetrical filling in T2G set, right? And the answer is T2G set is already suffering lesser repulsion only, and that is why it is in lower energy level, right? So obviously having unsymmetrical filling in T2G set is not going to have much of an effect. It is not that significant, right? So please understand that only if I have unsymmetrical filling in EG set, that contributes to Jahn-Teller distortion, right? So now we'll take these two cases specifically, right? And I'll try to chalk out how exactly the bond lengths are changing, right? Actually, if you look at one of them, it will be sufficient. Okay. So let me take the first case, that is, I have an unsymmetrical filling like this, right? So this kind of filling generally happens in when I have Cr2 plus and Mn3 plus weak field complexes, with weak field ligands, sorry, right? So when I have Cr2 plus and Mn3 plus with weak field ligands, this kind of unsymmetrical filling case is possible, right? So whenever you have this, remember that I am not going to have all the 6 bonds to have same bond length, right? Okay, now I have 2 orbitals here, that is dx squared minus y squared and dz squared, right? So for now, let's assume that there is no restriction. I can either put the electron in dx squared minus y squared, or I can put the electron in dz squared, right? So let me assume that the electron is going to go to the dz squared. So the electronic configuration is like this: dz squared 1 and dx squared minus y squared 0. I am going to take this case, right? So we'll see now what happens. Right now we know that I have an extra electron in dz squared and not in dx squared minus y squared. Okay, so let me draw octahedral complex, right? So let me assume that this is the z direction, right? And this is z, this is minus z, right? So now hope you know what are all the directions of ligand approach in an octahedral complex. There are going to be 6 directions of ligand approach, and we'll just put it along: x, minus x, y, minus y, z and minus z. These are all the directions of ligand approach. 6 directions, 6 bonds, right? Now where I have put the electron, I have put the electron in dz squared, correct? So can I say, if there are going to be 6 directions, but there are going to be 2 directions, that is z and minus z, and along these directions if the ligand is going to approach, I am going to have more repulsion suffered. Why? Because I have the unsymmetrical filling of electron happening in dz squared, right? So along z and minus z, the bond is going to get somewhat elongated, again because of higher repulsion suffered due to the presence of electron in the dz squared. Right, fine. So now what happens in other 4 cases, that is when I have x, minus x, y and minus z, I don't have any electron left there to increase the repulsion furthermore, right? So there the ligand will be able to approach a little bit more closer, right? But in the case of z and minus z, due to higher repulsion, the ligand will not be able to approach the metal atom in that much closer way. But in x and y directions, it will be able to approach closer. So what is going to happen because of this? Definitely there are going to be 2 sets of bond lengths. Two bonds are going to get elongated, and what are the elongated bonds here? Which are along z and minus z, because I am going to have more repulsion, right? And I am going to have 4 shortened bonds along x, minus x, y and minus y, right? So let me chalk it out. Along z and minus z, due to higher repulsion, 2 long bonds, right? And along x and y direction, the ligand is going to approach still more closer. I am going to have 4 short bonds, Now this happens when I have electron in the dz square. No problem. Now this phenomena is what is called as Jahn-Teller distortion, distortion of the bond lengths. Not all the bond lengths are going to be same, right? Now if to give you a better picture, let me put the electron in dx squared minus y squared now. So now I am going to have this configuration, dx squared minus y squared 1 and dz squared 0. No problem, right? Now again I'll draw the octahedral complex. So let me mark the directions. Assume that this is x, this is minus x, this is y, and this is minus y, and this is z, right? Okay. Now the electron is there in dx squared minus y squared. So can I say whichever directions I have ligand approaching in x or y direction will suffer more repulsion, because the electron is there in dx squared minus y squared orbital, right? So there are going to be 4 directions of ligand approach in such that I have the repulsion is increasing, that is x, minus x, y and minus y, and along these 4 directions the amount of repulsion is going to increase. So the ligand will not be able to move that closer to the central metal atom. But when I go to the other 2 directions, that is z and minus z, since I don't have much repulsion, the ligand will be able to approach the central metal atom a little bit more closer. So can you tell what are the consequences in terms of short and long bonds? Along x, minus x, y and minus y, repulsion is higher, not able to move closer, so 4 long bonds, right? And along z and minus z, it is able to move closer because of lesser repulsion, so 2 short bonds. This is what happens, right? Now the next question which comes is, sir, if, okay, we understood both of these, but if at all a case comes where I have to put electron either in this, that is dx squared, x squared minus y squared, or dz squared, where should I put, right? The answer is, you have to put the electron in such an orbital which will suffer lesser repulsion, so that there is not much complications, right? Now how do we do this? Now let me take both these dx squared minus y squared and dz squared. So if I take dz squared, right, now there are going to be 2 directions of ligand approach which is going to get affected, that is z and minus z, right? Now if I take dx squared minus y squared, there are going to be 4 directions in which the amount of repulsions are going to increase, and we know what are all the directions, x, minus x, y and minus y, right? Now I told you, you have to put the electron in an orbital which will suffer lesser repulsion. So obviously from these 2 you can understand that I will put the electron in dz squared, because there are going to be only 2 directions in which the amount of repulsion are going to increase. If I put the electron in dx squared minus y squared, there are going to be 4 directions in which the amount of repulsion will increase, right? So if you have a choice of putting the electron in either this or that, I will prefer to put the electron in dz squared, because the amount of repulsion is going to be somewhat lesser than the other case, right? Okay, now we will take the other case, that means we have 2 cases of unsymmetrical filling. We saw 1 case, and in that again 2 cases. So the next case of unsymmetrical filling can be like this. Right, so this kind of distorted or unsymmetrical filling happens in case of Cu2 plus complexes. Generally the beautiful example I can give is Cu H2O 6 times 2 plus. Here copper is in plus 2 oxygen state, definitely you will see this kind of unsymmetrical filling. So here also I am going to have Jahn-Teller distortion happening, as exactly same in the case of the previous case. I'm going to have longer bonds, shorter bonds, right? So I think I'm able to give you a very good picture of what exactly Jahn-Teller distortion is, right? So if you have any more queries, if you have any more doubts, please put them in the comment section, right? And if you like the video, please do like it, share and subscribe. Thank you so much.